This is a note, okay. So look, we can make connection between A and D, A and C, and we also can make connection between C and B. Okay, we can make connection between C and B, as well as we can make connection between B and D, but we cannot make connection between A and B. Look, if I make a connection between A and B, this is the path, so there is no any variables, right? It is the resistance of this bar. If I make a connection between C and D, that is going to be the maximum resistance of this coil. So wherever you move this connector, it is not going to, or this sliding key, it is not going to have a variable resistance. Okay, clear? So here continuous values of resistance can be obtained, but the value cannot be read. The value cannot be read. Okay, noted. So that is one way of doing this experiment using the ammeter and voltmeter. Then we can use, and that's case 2, we can use the ammeter and a resistance box. So that is case 1, case 2, case 2, using ammeter and resistance box. So this is the circuit. Let the EMF of the battery be E and current I. Internal resistance is R. So if we write the equation for this circuit, in this circuit, the equation is going to be E is equal I R plus simple R. Now my independent variable, who am I going to change? I am going to change the resistance value. Okay, I am going to change the resistance value. When the resistance value changes, the current is going to change. Therefore, my independent variable is R, and my dependent variable is going to be I. So we have to bring R to the x-axis and I to the y-axis. So let's subject I. If I subject I is equal E over E over R plus R, E over R plus R, but there's a problem. Here, I'm not able to I'm not able to separate this R. Okay, therefore, let's get the reciprocal. So 1 over I is equal R plus R over E. Or otherwise, I can write this one as R over E plus, no, I straight away write R plus R over E. So let's separate the denominators and write it as 1 over I is equal 1 over E into R plus R over E. Now we get or we obtain a graph in the form of y is equal m x plus c. So plot this graph. We are going to plot the graph between R and 1 over I. So we obtain a y equal mx plus c graph. So this is the intercept c and this is the gradient m. Okay. Intercept c is equal 1 over e. Therefore, e is equal to 1 over c. And look at the, sorry, that's the gradient, right? Gradient. So 1 over m. Look at the intercept. Intercept, we have c is equal e into 1 over e. So 1 over e is the gradient. Then r is equal intercept over the gradient. Okay, then we can determine the internal resistance and the EMF. Have you noted? Once you have noted, raise your hand. Once you have noted, let me know. Raja and Shahama. Okay, what is this resistance box? So here, how are we going to change the resistance? From the resistance box, from the resistance box, plugs are removed. Plugs are removed one by one by one, and the corresponding ammeter reading is obtained. Okay, not so what is this resistance box? In a resistance box, it is a box. As the name suggests, it is a box. Here you can connect and here you have keys, plugs. Okay, you have plugs. These plugs can be removed. Plugs that can be removed. To understand how it works, let's look the plug. Let's look one of the plug, the cross-sectional wave. So if we look from this side, if we section this, if I cut this from this section, if I cut from this section, then this is how it is going to look. We have a very thick plate. We have a thick plate of a conductor. So this is a conductor. In this conductor, we have made some holes, okay, to plug in these plugs. So plug in these plugs. And here we have a resistor. Here we have a resistor. Let's say the resistance is R1 and this resistance is R2. Now, if I remove this plug, then I have removed this plug, okay? How will the current pass? So I have removed the plug. So soon after I remove the plug, the current has to pass like this. Here it will pass through this plug because that is a conductor. The plug is a conductor. On the top it is an insulator. On bottom it is a conductor. Now this has to pass through this. Okay. So what is the resistance here? So here R is equal to R2. If R1 is also removed, then R is equal to R1 plus R2. Is it clear how the resistance box works? Is it clear how the resistance box works? So what is the advantage? What is the advantage of resistance box over rheostat? Okay, Saja, here, Saja, it's like this. We have these plugs, okay? These plugs are made up of insulator on the top and a conductor at the bottom. So this is a thick conductor, okay? So when it is a thick conductor, we know the resistance is going to be very less. If you plug in this, and here, when we plug in this, the current will go through the plug. The current will go through the plug. It won't choose this path. When we compare these two resistors, this is high and this is very low. So the current wants to choose this path. Okay. Although there might be a very small current through this. If you remove the plug, now the current is forced to go through this resistor. So what is the resistance now? According to this diagram, the resistance is R2. Let's say you remove this plug also. You removed this plug too. If you remove this plug, then the resistor R1 and R2 come in series. So the equivalent resistance become R1 plus R2. You plug in this plug and remove this only. Then the resistance is R1. Is it clear, Saja? So when we compare this resistance box over rheostat, there are some disadvantages and advantages as well. Okay. So here, can we get continuous resistance value? No, there are only a fixed amount of values. So cannot obtain continuous values of resistance. But what is the advantage here? Here you know what value you are going to get. But the value of the resistance can be obtained. Okay. Now think about this experiment. In this experiment, can we use a rheostat? Think about this experiment and let me know. Can we use a rheostat? So that is note number 1. Note number 2. Rheostat. Rheostat cannot be used for this experiment since the value of R has to be obtained or has to be read. Okay, are the points clear? Raja and Shahama. Okay, so case number 3, we used ammeter, voltmeter, ammeter resistant box. Now case 3, we are going to use voltmeter and resistant box. So this is going to be our circuit. So here we know that we can apply, if we apply the Kirchhoff law for this loop, we get E is equal I R plus simple R. But when we check the potential difference across this resistance, we get but V is equal to IR. Therefore, E is equal IR. We have to somehow eliminate I. Okay. So V is equal IR. That means we get R plus R. Now E is equal V plus V R over R. Uh, okay, what is the dependent and what is the independent? What are we going to change here? We will be changing the values of R and V is going to change. Therefore, V is independent and R is independent and V is dependent. R is independent variable, and V is dependent variable. So let's subject V. If I subject V, I get V is equal ER over R plus R. Again, we have the same problem. We are not able to subject, or we are not able to get R in place of X. Therefore, let's get the reciprocal. Then 1 over V is equal R plus R over ER. Let's write them as separate denominators. Then I get 1 over V is equal R over ER plus 1 over E. So we get a graph in the form y is equal mx plus c. So if you obtain the readings for R and V and plot 1 over R versus 1 over V, we obtain y equal mx plus c graph. From that, we will be measuring the intercept and the gradient. We'll be measuring both of them. The intercept is equal to 1 over E, then E is equal to 1 over C. Now let's look at the gradient. M is equal R into 1 over E. M is equal simple R into capital intercept C. Then R, internal resistance, is gradient over the intercept. Okay. So here also we remove the plugs of the resistance box is removed one by one, and the corresponding voltmeter reading is obtained. Okay. Here also, can we use a rheostat? Once you have noted, let me know. Saja and Sarah. How about a rheostat? Are we able to use a rheostat here? Can we use a rheostat for this experiment? So when do we use a rheostat? And sorry, when do we use a resistant box? When do we use rheostat? We use resistant box if we want to get the value of the resistance. So here, do we need the value of resistance? Yes, we do, right? Here, because we want to measure, we want to get the reading of R. Therefore, here we use a resistant box. But in the first case, do we measure the resistance? No, we didn't measure the resistance. Then we can use a rheostat. Okay. Can you make one change in all the diagrams? Shall we add a switch? Sorry, I forgot to add a switch in all these. Can I add a switch to every diagram? Do you have space under the first experiment? A note. Oh, let's write it under this. In all three of the experiment, tab key, sorry. Yeah, tab key is used. Tab key is used. Okay, what is a tab key? It is like this. So you have a knob and this is the connector. Okay. If you press it hard, then the connection, we should press it really hard. Okay, really hard means to have a very good contact. It is pressed. So when you leave, the switch will automatically get open. So that is a tap key. So just draw a diagram of a tap key. Opens automatically, opens when not pressed. Okay. So what is the advantage of tap key? When we take the reading only, we need a current flow in the circuit, right? So other time we don't need a current flow. Okay, that is why we use a tap key. Tap key is pressed. Tap key is pressed sufficiently hard to have a good contact when taking reading. When taking reading, tap key avoids the battery getting discharged quickly by opening the circuit. Okay, is the idea of tap key clear? Why we use tap key and what is the purpose of it and how to use it? Once you have uh, made those changes, I mean adding a key and noted this, raise your hand. Please note it now. Sarah, okay. So in the past papers, you have a lot of questions related to these sections. They won't directly tell you which experiment we are using, okay? You must understand the situation. Is it case 1, case 2, or case 3? And you must understand what information do we need. So when you read the question, you can get the idea. Uh, Once you get the idea, you must use that relevant equation, okay? You get the relevant equation and subject the necessary term understand what is independent and what is dependent, and you have to try the question. Okay, so next let's go to a new topic, Wheaton-Bridge principle. Wheaton-Bridge. So Wheaton-Bridge, this is a concept that we have already studied. It is very close to something that we studied earlier. We have four resistors. We have four resistors. Three of them are variable. Three of them are variable. And one of them is unknown. And we have a galvanometer. We have a galvanometer at the center. It has a high resistor and a plug key. Okay. So this is a galvanometer, center zero galvanometer. Here this is connected to a circuit. So by adjusting R1, R2, R3 and R4 adjusting R1, R2 and R3 at a certain instant, no current flow through the galvanometer. Flow through the galvanometer. This is called the balance condition. This is called the balance condition of the circuit. Okay, so at balance condition, if we mark these with letters,